Hello everyone, my name is Misong Kim and I'll be presenting a paper titled FreeScene. This paper was presented at CVPR 2025 and it introduces a new framework that can take completely freeform inputs such as text or images, automatically convert them into a structured scene graph, and then generate highly controllable 3D indoor scenes based on that graph. Let me begin with an overview of the FreeScene system. FreeScene is composed of two major components. The first component is the Graph Designer. This module uses a vision language model such as GPT-4o to convert freeform user inputs into a structured graph. The second component is a diffusion transformer called MGDIT. This model takes the graph and the optional text input and generates the final 3D scene. These two components work together to turn flexible user inputs into controllable and well-structured scene layouts. Here I will explain the problem that FreeScene aims to solve. When we want to generate a scene that accurately reflects a user's intention, we need a method that is both easy to use and highly controllable. However, current approaches always sacrifice one of these aspects. Text-based methods are easy and natural to use. However, they often fail to place objects precisely, and spatial relationships can easily be incorrect or inconsistent. In contrast, graph-based methods provide very precise control. But the downside is that creating a scene graph manually is difficult and extremely burdensome for users. In short, text input is convenient but lacks control, while graphs are precise but hard for users to create. FreeScene attempts to overcome both limitations at once. The goal of this research is clear. The authors aim to build a unified framework that can take any type of input, convert it into a graph automatically, and then generate a controllable 3D scene from that graph. This eliminates the need for users to manually create a structured scene graph, while still giving them precise control over the final layout. The overall process consists of 3 stages. In the first stage, the graph designer interprets the user's input and constructs a partial scene graph. This graph contains a list of objects, a list of spatial relationships, and a short textual description of the room. In the second stage, the MGDIT model completes the full scene layout. It infers the positions, sizes, and rotations of the objects. In the final stage, the system retrieves actual 3D furniture models from the 3D furniture dataset to construct the final rendered scene. Now, let us take a closer look at the Graph Designer. This component is built on top of a powerful vision language model. Because models like GPT-4o can understand both text and images, they are well suited for transforming freeform inputs into structured information. The Graph Designer leverages this capability to extract objects and spatial relationships in a consistent manner. The Graph Designer extracts 3 kinds of information from the input. The first is a list of objects. For example, the model may identify a bed or 2 nightstands and a wardrobe. The second is a list of spatial relationships. For example, a nightstand may be to the left of the bed and another may be to the right. The third is a textual description of the room. This provides contextual information summarizing the scene. By combining these 3 elements, the system constructs what is called a partial scene graph. This graph becomes the main conditioning signal for the later stages of the pipeline. The core of the Graph Designer is not just the vision language model itself, but the way the prompt is designed. First component of the prompt is the task description and the constraints. This tells the model which objects may appear, which spatial relationships to extract, and what the final graph format must look like. The second component is the multimodal input. The prompt includes the user's text, image sketches, floor plan diagrams, or any combination of these. The third component is the rule explanation. This part explains how the model should determine the viewpoint, which objects are actually allowed to be extracted, and how the model should judge spatial relationships such as left, right, front, and back. The fourth element of the prompt is chain of thought guidance. The model is instructed to think step by step in a specific order. It calibrates the viewpoint first, then extracts the objects, then extracts relationships in a consistent way using depth-first search, and finally refines those relationships before constructing the final graph. The fifth element is one-shot example. This gives the model an exact template that it must follow when producing output. The authors also explain why DFS is used. If the model tries to extract all pairwise relationships at once, the output often becomes messy, contradictory, or incomplete. DFS encourages the model to extract relationships in an organized and consistent sequence, which greatly improves accuracy. Now, let us move on to the second major component, MGDIT. The inputs to MGDIT include the object categories, the relationship graph, and optionally a text description. All other attributes are given in a noisy form. The outputs include the positions, sizes, and rotations of all objects, the feature index of the furniture, discrete tokens for relationships, and finally the complete scene layout. This model performs mixed diffusion, meaning it handles both continuous values and discrete values at the same time. This is essential because 3D scenes involve both numerical geometry and categorical information. Traditional diffusion models typically handle only one type of variable, either continuous or discrete. FreeScene combines the two. The continuous part follows the standard DDPM process. Noise is gradually added, and the model learns to predict that noise. The discrete part follows a D3PM process. Categorical tokens change over time. Some of them stay the same, some become masked, and others transition to different categories. This process is a discrete Markov chain. By combining these two processes, FreeScene can generate both geometric attributes and categorical attributes together. Here we look at the internal structure of the MGDIT network. Each object is represented as a node, and the node embedding contains noisy versions of all object attributes. Each relationship is represented as an edge, and edges are also embedded with noise. The model uses a graph transformer block, which includes graph attention, cross attention for text, and FILM conditioning that allows relationship informations to modulate the node features. It also uses adaptive layer normalization to inject time-step information and text conditioning. The network outputs two types of predictions. One is continuous noisy predictions for geometric attribute. The other is probability predictions for discrete categories and relationship tokens. One of the greatest strengths of MGDIT is that the model can selectively fix some variables and regenerate others. This allows the same model to perform many different tasks. For example, if the object categories and relationships are fixed, but the positions are regenerated, this becomes a rearrangement task. If only the categories are changed, the system performs style modification. If only the relationships are given, it becomes a graph-to-scene task. And if only a text description is provided, it becomes a text-to-scene task. This flexibility makes the model highly versatile. In the text-to-scene experiments, FreeScene demonstrates clearly superior performance compared to previous models. Earlier methods often failed to interpret text accurately or suffered because the graph generation and scene generation modules were separate. FreeScene avoids these issues by converting text into a graph first, and then generating the scene from that graph. This leads to both higher quality and stronger controllability. Finally, the authors discuss several limitations. First, the graph designer relies on a vision language model. When there are many objects, the model may still miss some relationships. Second, MGDIT sometimes struggles to control position and rotations with perfect precision, which may result in slightly unrealistic layouts. Third, the dataset used for training, such as 3D front, contains imperfections that may cause overfitting or representation bias. Despite these limitations, FreeScene provides a unified and effective solution for converting freeform inputs into structured graph and controllable 3D scenes. This makes it a meaningful step forward in 3D synthesis. That concludes my presentation. Thank you for your listening, and I would be happy to take any questions.